In this video, we're going to switch gears and look at another system call function that's very important, and it is the fork system call. And what fork is going to do is so interesting and unique. I want to give you a chance to try and reason through it before I explain it to you. So let's jump into the fork.c example code and go ahead and add some code to try calling it. So I'm in my fork file and I set up an if statement, if fork. And here I'm going to print non-zero, and actually let's do printf non-zero and new line, else printf 0 \n and a new line. All right, so we've got our fork function call here, and the question to you is, what do you expect the output to be? Or given that you don't know what fork is going to return, what do you expect will be printed to your screen when you run this program? So think about that for a second, try compiling it and running it, and pause the video at this point before you continue on. All right, so I'm guessing you weren't expecting what you saw. And in fact, if you're stumped by what you saw, you're rightly so. So let's try this out. All right, so I'm going to gcc fork.c and try running it. Wow, that's kind of weird. Well, first of all, it's really strange that 0 printed after learn CLI $. That's strange. But this time around, we got a slightly different output, non-zero followed by 0, and then the output there. That's bizarre. Why are we seeing two printed values, one in the if branch, one in the else branch of an if then else statement? Both of them are being evaluated. What in the literal F is happening here, right? This breaks everything we know about how a program should evaluate when interpreted by a computer, right? Like this should only be able to go in one or the other direction. What is happening here? So fork is a function call that's really interesting, and it asks the operating system to do something for us, right? But before we get into what exactly it's doing, let's just remind ourselves of a process's memory, right? So a process, when we run this process, and I'm going to name this a.out, it's got some areas of memory. We've already talked about these things, so I'm going to fly through this. It's got its code, which is in the text section, right? These are the instructions. It's got its static memory. We've got our heap memory, right? I'm just trying to very quickly get us into thinking through what all of these things are. And in this case, with this very simple program, there's not a whole lot here. We've got our stack that's growing down. Our frames for function calls are in the stack. We've got some arguments. And this is a hand-wavy, high-level representation of what we have in memory. Now, the program also has as a part of its state, or the process also has as a part of its state, where it is in the program at any given time, right? The current line that's being evaluated or the control pointer, right? And so what we're thinking about here is what happens when this fork function call is encountered. Well, we know that this process is going to have some state in memory that's made up of all of the values in its memory, including its program code. And so what fork says is, hey, operating system, I want you to make a clone of me. Like I want you to make another one of me. Copy me and make a clone of me in memory so that there's two of me running rather than just one of me running, all right? So what happens is the operating system says, okay, we're gonna make a clone, right? Well, if I could draw a straight line here, we're gonna make a clone. And that clone is gonna have all of the same things that the original one has. For the most part, when you get to operating systems, you'll see that there's a few details here that I'm glossing over. But assume that like effectively every byte that was in the important parts of memory for the original a.out process are being cloned to another process, right? And it turns out through the virtual memory system, this is actually a very very efficient copy. We're not actually copying things in memory like byte by byte. There's some clever tricks that you'll learn about in operating systems that make this an efficient process. But from our vantage point as users of the system, Yeah, definitely, we've got two copies of these things such that if we were to write to one, it would not have any impact on the other, right? But if we were to read from either of these two copies of the process in memory, and I'm going to name this process, I'm going to name this parent, process P, and process C for child. Right? If we were to read any contents of memory from either of these processes in this fork, after this fork function call is evaluated, immediately after it, they're going to be the same. Right? So the key difference between these two things is that when fork returns, it returns to both processes at the exact same point. Right? We reach the same point in fork. If there was code above this, we would have skipped right to it in the child process. And actually, I'll write out child here and parent here. We would have skipped right to this function call fork in the child, and both processes are going to return from this exact same point, but how they return is going to be different. So the parent is going to get a non-zero return value. All right, the parent is going to get a non-zero return value. So I'm going to make a note of that. Return value is non-zero. And what it's going to get back actually is the process ID of the child. Right? So it's going to have a handle on that child process's ID in case it needs to send it a signal or wait for it to complete or something like that. Now the child is going to, when it returns from this call to fork, it's going to have a return value of 0. Right? So this will be the child completing or the next line of the child that gets evaluated. Right? So fork is a function that you call once and it returns twice because you've actually spawned up another process in your operating system. And now you have two copies of a.out, the program, running side by side and concurrently in your system. One just has, from the only difference at this point in this example program is they'll have different return values from this function call to fork. All right, so if we want to take this a little bit further, one of the things we could do to convince ourselves this is actually how it works is let's try adding a printf statement here that's just the word done or the string done. What do we expect this to be? Maybe I'll add a new line character there. How many times do we expect the keyword printf done, that line of code, to be evaluated? Well, let's try it out. So I'm going to compile my fork.c again and run it once more. And notice that done is printed twice because both processes continued on from where that fork function call was encountered until they reached the end or the exit of their process, right? So if we wanted to imagine how this might have looked, we can take a look at what we're going to call as a happens before diagram, right? So when our process starts, this is going to be P0's timeline. We encounter a call to fork, right? And so when this fork call is encountered, the parent process receives back the child's ID, which is non-zero or a truthful value, right? And so the parent continues on, and the child process in that call to fork has a 0 value in its return value, and it would continue on from that point. And so both of these processes then would move in a different direction in this branch, and finally both would print the word done after the end of it. You don't have any hard guarantee from the operating system which process is going to continue first or the order in which they're going to concurrently run thereafter. In fact, that's the thinking about problems related to concurrency between two processes is something you'll learn about in distributed systems and operating systems to come. All right, so now you might be wondering, well, why would I ever need to use this? This seems kind of crazy. I can't really fathom a use case for this. Well, if we think back to the exec function call, there's something really interesting that makes these two functions complementary to one another, right? Exec was a function that you called it once and it never returned. Fork is a function you call it once and it returns twice and has two different processes. So what we're going to do is combine these two concepts, these two orthogonal, meaning unrelated concepts. We're going to bring them together to give us the ability to have one program that starts another program as a new process and then waits on that program or that process to complete. Right? So let's take a look at how we can bring these files or these concepts together in the exec file. So I'm going to open up exec.c And I'm going to add an include here for sysWait, which will allow us to wait on, gives us some functions that allow us to wait on a process completing. So remember in this example, what we did was we were demonstrating the use of exec CVP. So we are executing grep here. And the downside to this was like this program would never reach the print statement done, because as soon as we called exec, if it's successful, that exec is taking over this process's memory entirely, right? It becomes grep, and we no longer, anything that came after this is not going to be there. But with fork, we can make a clone first and then let the clone be taken over by exec, right? So let's try this out. I'm going to add a fork. So if the result of a fork is equal to 0, right? So we talked about the return value of fork before. And the return value of fork says this is the child process. If it is 0, that means we know that we are in the child process return value of fork, right? We're no longer in the parent, we're in the child. And what the child is going to do is begin the grep program, right? Now in the parent process, what we want to do is wait on our children to complete. Right? So I'm going to give a wait system call. And if you read the documentation for the wait system call, there are a number of options here. And by passing 0 or null as what we're waiting on, what we're saying is just wait on any process that's a child of mine to complete effectively, right? But there are some, you've got a lot of control over this, right? You can imagine forking many children processes and wanting to wait on specific ones to complete or in specific orders for them to complete in. There's a lot of nuance here that we're glossing over with some hand waving. But the idea is if we fork in the child and we're in the child process, what we're going to do is set up our redirect table. We don't need that redirect table to be anything about it to be happening in the parent process, right? And then go ahead and kick off, hand over this process to grep. But in the parent process, what we're going to do is just wait on our children. In this case, there's only one, our child, to complete, right? So let's try this out. And so now I'm going to gcc exec.c. I'm going to clear my screen and /a.out. And so notice I am able to type at standard input. So standard input is being piped to grep right now. And I can do things like hello, nothing's going to be printed. But this, remember, in this example, we set up grep to look for lines that end in C. So if I do like hello.c or another line.c and another foo, and then control D to end my input, notice that done was printed. And that done print statement came from our program a.out. The parent process was waiting on grep to complete, which it only could as soon as standard input had been finished and given the end of file input. And so now if we were to look in our directory, we can see in redirect file descriptor.txt, there are those two lines that we just entered as inputs to our program a.out. And so with these fundamental building blocks, with fork being able to spin up a child process that's a complete clone of the current process, and then exec being able to take over that clone process and make it a process for another program, we have the fundamental building blocks of working with a very simple shell. And then with the dup2 system call, we're able to control, well, how are standard inputs and outputs hooked up to different things. And in the next lecture, we're going to look at how do we create pipes, and how do we actually bring this all together once we have our parsed grammar from a line of input, and we have a parse tree that indicates here are the commands and here's how they're connected together by pipes. We can take that and process it recursively using these system calls to form our graph of processes that are connected to one another via these file input-output streams, and run those programs, wait for them to complete, and then prompt the user for the next line. So we have all the fundamental building blocks except for the pipe construct in our wheelhouse now, and all we need to do is connect them together.